And our last speaker of the session will be Guillaume Bourdarot. If you're there, I'll just stop sharing our screen here. Please go ahead and share your screen.
Can you see my screen, hear me, and see my pointer?
Yep, it's all looking good here.
Cool, okay.
Okay, so Guillaume will be telling us today about optical aberrations and systematic analysis for astrometry in gravity. So please take it away.
Thank you very much then for this introduction. And yeah, I would first of all like to thank the organizers and participants for the nice series of talks throughout this week and the nice results that have been shown. And today I will present the work related to optical aberrations and systematic analysis in gravity. I present this work on behalf of the whole gravity collaboration. And in particular, I would like to acknowledge the work of Felix Wiedmann and Julia Stadler on this topic. As an introduction, as you probably all know, gravity is a leading instrument to achieve high precision astrometry at the LTI, which is key for several science cases, among them two prominent science cases. First, the measurement of position of stars and their orbital motions around the galactic center. This was already presented in the talks by Felix Wiedmann and Antonia Drescher this week. This high precision astrometry is also very interesting in the field of exoplanets. And here is a schematic which has also been shown by Sylvestre Lacour of the Beta Pictoris system, in which, thanks to the high precision astrometry, we can now even see the three-body interaction in this system. So see the perturbation of companion C on B, which is for which astrometry is the key. There are also so astrometry is an interesting product in this dual field mode, but there are also it is also an interesting technique for planet detection through stars reflex motion. And in particular, there is an ongoing program on JG65 with gravity, and this method of detection was also presented earlier by Keegan and Tyler Garner this week. So astrometry is important, and the astrometry in gravity is made of different blocks. So gravity is a dual field instrument, which means that there are it combines two interferometers, let's say at once. One channel, which is a fringe tracker, which allow to follow the fringes, and one channel, which is a science channel on which we integrate the signal. Gravity has its own metrology system, which enables to measure the differential OPD between these channels, which makes this instrument, which allows this instrument to do phase reference astrometry. And the targeted and the precision of the instrument is of the order of 10 to 30 microarc second, as was also detailed in the sensitivity budget of gravity. And just to give an order of magnitude of the numbers that we will talk about in this presentation, this represents a typical relative precision of 5 times 10 to the minus 4. If we take the typical separation of S2, for which the precision can be accounted on different points in the astrometric budget, among which aberrations are an important point, and this is the focus of this talk. And in particular, as we will see in more detail, the aberration we'll talk about here concern the objects. The objects are at large separation in the field of view of the fiber. So typically binary stars with a separation of the order of the field of view of the fiber, or single object for which the position is not perfectly known, for example, in the dual field mode with exoplanets. So the model of aberrations considered here is the following. The wavefront gets distorted in the pupil by aberrations. Then it is focused in the focal plane or the image plane, and then coupled to the fiber, which is then directed to the beam combiner. So this pupil plane aberration can be expanded on a Zernicke basis to account for the OPD in the pupil plane. And then once it's focused on the fiber, can be overlapped with the Gaussian mode of the fiber. And here on the right-hand side, you can see, so here the first schematic is a wavefront without, so it's a wavefront in the image plane without any distortion, so with an airy pattern and a Gaussian profile, here with a tilt, and then with an astigmatism. These aberrations are not the only one which enters into account, and it's also important to take into account the focal plane or the image plane aberrations. And here on the left-hand side is a typical illustration of the effect. So here you can see the image plane wavefront with only pupil plane operations, and here with the addition of a fiber tilt. So here the main aberrations in the focal plane that we will talk about are the defocus of the fiber and the tilt of the fiber, which are shown here. And this can also be seen on the amplitude map. So this focal plane aberration overall looks like a contraction of the PSF. So to measure and to correct this aberration, the first step was to do the mapping of this aberration, and this was done with the gravity calibration unit. So at the entrance of gravity, there is this module which can produce a beam of light equivalent to a star, but for calibration purposes. So the way the measurement is done, that this source is scan the field of view of the fiber. And for each point of this scan, the measurement of the phase allow to reconstruct the phase map and the amplitude map of the aberrations. And here on the middle part is the actual measurement of these phase aberrations on each beam of gravity, so on the 4 beam at the input of gravity. The next step is then to fit the Zernicke coefficient to this measured aberration map. And this is shown, so according to the model that we presented just before, and this is, and here on the left-hand side is shown the residual between the fit of the wavefront in the image plane and the measurement with the calibration unit. Then, so this gives a typical aberration map for each beam, for which then we have to take into account 2 other effects. First, the obscuration, the central obscuration of the pupil due to M2, which modifies the profile in the image plane. And then the turbulent smoothing. So as the atmosphere introduce a typical tip-tilt jitter, this can be accounted as a Gaussian profile, as a Gaussian kernel, which is convolved with the aberration. So the typical fitting of the aberrations and the typical RMS of the residual here is of the order of 1 degree on the pupil seen by gravity. Then once these steps are done, this can be applied to the model fitting of the source in order to correct the aberration in the fitting of the astrometry. This was done in the first step after the measurement on sky with a test target. So that was binary star with the ATs with a typical separation of 200 milliarcsecond, sorry, because this is a field of view of the fiber on the ATs. And here is shown the typical separation of the binary on the fiber, on the entrance of the fiber. And here on the left-hand side is the measurement of the position of the separation of the binary before and after applying the correction of the aberrations. So here you can see that there are two effects. First, an offset and a dispersion, which are both reduced when applying the correction with the aberration maps.
2 minutes, 2 minutes.
2 minutes, perfect. So then, and this is the last part of my talk, this was, after this test campaign, this was successfully applied to the observation of S2, so the star orbiting the galactic center, and in particular for the data set at large separation, so on the order of 50 mass, when S2 was really at the edge of the field of view of the fiber, for which this effect of aberration is most prominent. And here is the correction of this effect. So in gray are the individual astrometric points, and in blue and black the average of this individual observation, and then this value is the correction applied to the position of S2. And what is nice is that applying this correction also show to provide very consistent result with the dual beam measurements for one given point here that you can see, which show that this is working very well. And the main application science of this measurement was in refining the measurement of the distance to the galactic center with this 5 times 10⁻⁴ precision. So as a conclusion, and I will finish with this, static aberrations that we talk about during this talk are important to take into account for objects at large separation in the field of view of the fiber. In gravity, there is a consistent measurement and correction of this effect. It was already applied to the measurement of the separation of S2, in particular for the distance to the GC. But in more generally, this can be applied to any cases when very high precision on astrometry is required at large separations. So, for example, with exoplanets, where the planet is when the position of the planet is not known, or for high precision astrometry in large separation binaries. And this is also part of the next step of this study is also to study the impact of aberrations on the internal metrology and also the effect of the non-common path aberrations in the astrometry. But I thank you all, and I'm done.
Okay, questions? Yes, up there. Please state your name and affiliation.
Hi, Guillaume. This is Tyler Gardner from University of Michigan. I was curious, are there plans to implement these corrections straight into the gravity pipeline, or is it something that one has to do afterwards?
For the moment, it's done afterwards because it's really taken into it's really handled when you fit the visibilities and the visibilities of your observations and your model, let's say. It's not done in the pipeline, it's really the step after.
Okay, thanks. Great work.
Any other questions? No? I have to admit, Tyler asked a question I was going to ask, so yeah, it's interesting. So will this be available, if it's not part of the standard pipeline, will it be available to the community to apply to their observations, even if it's a separate routine?
I think that for the moment, since it depends, for example, on this aberration map, I think that the best way is to get in touch with the core team working on that, because it's a proper way then to handle these aberration maps and apply it to the data. So these maps are, I mean, are part of the routinely fitting procedure of the GC. So it's something which is now used on a daily basis.
Okay, something to bear in mind if you're doing astrometry with gravity. If there are no more questions, can we thank our speaker and all the speakers in this session again?
Thank you.